Let's take a look at example 3 from 15.1. We're asked to sketch some vectors in the vector field v of x comma y comma z equals 16 minus x squared minus y squared k, where x squared plus y squared is less than or equal to 16. Let's proceed like we did with the last couple examples, where let's figure out specifically where the vectors would have a consistent magnitude. First of all, if we look at where this vector field is going to be good for, it's for x squared plus y squared less than or equal to 16. That would be a circle in the xy plane centered at the origin with a radius of 0. So all of the vectors we're talking about would have projections onto the plane that would lie inside of that, or on the boundary of that circle of radius 4. If we look to see where these vectors would have a constant magnitude, remember the magnitude of a vector or vector valued function is the sum of the square of the component functions, and then we square root that. Here, v only has one component function, which is just k, so all of the vectors in this vector field are going to point upward, or potentially downward, that is. But we'll see in a minute that they're all going to be upward. This is 16 minus x squared minus y squared squared is going to be equal to a constant. The square root and the square cancel. From algebra, we know that they usually cancel, leaving us with the absolute value of the expression. However, because x squared plus y squared is less than or equal to 16, this quantity will always be positive, so we don't need to add the absolute value bars onto this. I'm going to take the variables to the left-hand side. I'll bring the constants to the right-hand side, and what we get is 16 minus c is equal to x squared plus y squared. This ends up being a circle. It's a circle centered at the origin, whose radius would be the square root of 16 minus c. So one of the things that we can quickly kind of discern in terms of the values and the magnitudes of these vectors is, because r has to be, a positive value, and magnitude itself, c, can't be negative, the magnitudes of these vectors will be bounded between 0 and the square root of 16, which is hold on, it should be 16 and 0 and 16. So let's go ahead and plot a few of these. For example, if I plot, let's say, the vector at 4, 0, 0. This would be 16 minus 4 squared minus 0 squared k, which is 16 minus 16, which would be 0k, which is just going to be the 0 vector. So at one point here, this vector coming from 4, 0, 0 is going to have a magnitude of 0, which is the 0 vector. So we see that on the boundary, on that circle of radius 4, if you pick any point there, or any point that projects to that of the form x, y, and z, it's going to have the vector, the 0 vector. We know that, from what we just showed a moment ago, that the vectors are all going to have the same magnitude on a circle of the same radius centered at the origin. Let's pick another vector. So what about the vector at the origin? If I plug 0, 0, 0 in, we would get 16 minus 0 squared minus 0 squared k, which would be 16k. So at the origin, what we would have would be the vector k, which would point up and coincidentally would have magnitude 16. Let's pick another point. Let's say we'll do 0, 3, 0. If I plug that into our vector value function, this is going to give us 16 minus 0 squared minus 3 squared k. That's 16 minus 9, which would be 7k. So at 0 and 3, we have a vector of length 7k, and then you can kind of figure out what's happening. As either x or y increases, this difference gets smaller, and so what happens is we kind of have like a cascade of vectors that get smaller at each foot point as we move outward along this circle of this particular radius. So as we move out, they're going to decrease until we get to the 0 vector on the boundary. And if you want to, you can kind of see this illustration is also presented in the textbook. The longest vector, the one with the greatest magnitude at 0, 0, it points up. As we move outwardly along any concentric circle, along the circles they have constant magnitude, but the magnitude decreases as we move to the boundary.